All right, welcome to section 6.6. We have dealt with several different types of problems that involve integrating fractions. So we had the ones at the very beginning where we took where it was you're dividing by a monomial, and we took it and we split up the fraction. We just got done with ln problems where you have the derivative of the bottom on top. We're going to kind of go through all the other techniques we need to deal with fractions in today's lesson. And this is a challenging section. There's such a diverse types of problems that it becomes challenging to know which method to approach or which method to take. Okay, so let me show you a couple of things we can do. So if you look at this one, this is not an ln problem, right? The derivative of the bottom is not on top. I also can't split the fraction up because there's two terms on the bottom rather than just one. If that happens and the degree of the top is bigger than the degree of the bottom or the same, then one method we can try is long division. And what we're really trying to do is trying to split that fraction up. Okay, so you guys did long division last year. Let me just remind you about it. What I'm dividing by goes in front, right? I'm dividing by x squared plus 2. What I'm dividing into goes on the inside. So we have x squared minus 4x plus 2. Okay, and when we start, we look at that first term right there. And I ask myself, what do I have to multiply the x squared by to get the first term right here, which is x squared? Well, that would just be 1, right? So put a 1 up there. And then you have to multiply the 1 by the whole thing, by the x squared and the 2. So 1 times x squared is x squared. 1 times 2 is 2. And then we have to subtract them. So minus, minus. By the way, I put the 2 over here to line it up with the like terms up above, right? 2 doesn't go with 4x, 2 goes with 2. Okay, x squared minus x. That comes out to be 0. And this one works out kind of nice. This won't always happen, but in this case, those come out to be 0 also. So I'm left with negative 4x. Okay, then we start over again. We're trying to find out what can I multiply x squared by to get a negative 4x. Well, that's not possible because the degree of the top, the square, is bigger than the degree of this, right? That's that 4x to the first power. So at that point, I know I'm done. So up here, I'm going to go, this is minus 4x over x squared plus 2. My remainder goes over what I was dividing by. Well, what I've done now is I can rewrite this. I've rewritten this integral in a different form. So now I have the integral of 1 minus 4x over x squared plus 2. And now I can actually take that integral and split it apart. I can split it into two separate pieces. So let's do that. Now I have the integral of 1 dx minus the integral of 4x over x squared plus 2 dx. All right, integrating 1 is easy. That's just x. Okay, this part's a little tricky, but think of all our different techniques. We know that the derivative of the bottom, the derivative of x squared plus 2 is 2x. Well, I've got a 4x up on top. So what I'm going to do is I'm going to think of 4x as being 2 times 2. Okay, and then I can take out one of those 2's out in front. So it'd be minus, I'm going to factor out a 2, minus 2 integral of 2x over x squared plus 2. Okay, now I've got the derivative of the bottom on top. This is just an ln problem. So my final answer is x minus 2 ln of, and it'd be the absolute value of x squared plus 2. X squared plus 2 is always positive, though, so I don't need the absolute values. So I'm not going to worry about those. X squared plus 2 plus c. And I've got it integrated. So that's one technique. And the way you usually do that when the degree of your top is bigger than the degree of your bottom. Okay, so if you look at number 2, this one's got a little trick to it also. When you're going to go break this, you can't really break this one apart again because there's 2 terms on the bottom. I got the square root of x minus 1. So what I'm going to do is try a little substitution problem. So I'm going to go like this. I'm going to set u, but this is a little bit tricky. Instead of setting it equal to the inside of the square root, I'm going to set it equal to that square root of x right there. So I'm going to say u equals the square root of x. Okay, now solve for x. So if I solve for x, I'd have to square both sides. So we'd have u squared equals x. Take the derivative of both sides. This would be 2u du. This would just be dx. Okay, now we're all ready for substitution. So let's come back up here and do some substitution. I have the integral. Oh, sorry about that. You guys will have to forgive me. I'm working from home, right? And so I'm using a little tablet thing here. It's a little bit different. So, okay. So we're going to come up here. We're going to do our substitutions. Now I have the integral of 1 over, in place of the square root of x, I put u minus 1. I have du. Sorry, I have 2u du. Erase that. So I have 2u du. Okay, so I don't have that square root anymore. I'm just going to simplify a little bit. I'm going to write it this way. I now have the integral of 2u over u minus 1 du. Okay, now if you think about this one, the degree of the top is the same as the degree of the bottom. So we just said when that happens, long division is a tool we can use to split it apart. So now I'm going to do some long division. I'm going to take u minus 1 and I'm going to divide it into 2u. So what do I have to times u by to get 2u? And that'd be 2. Now you got to multiply it by the whole thing. Be really careful with that. So u times 2 times u would be 2u. 2 times a minus 1 would be a minus 2. But I have to subtract them. That changes the signs. Those cancel out. So I have a 2 left over. Okay, so I come over here. I have the integral of 2 plus, because it's a positive 2, 2 plus 2 over, right, 2 is my remainder down here. So it has to go over what I'm dividing by. Okay, now I can just split that apart and do it piece by piece. So now I have the integral of 2 du plus the integral of, let's see, 2 over u minus 1 du. This would be 2u. Hey, the derivative of u minus 1 is 1. So I just want a 1 up here. So I'm going to factor that 2 out. Factor a 2 out of here, which should just leave me with 1. Okay, the integral of, it would be 2 times. Now I have the derivative of u minus 1 is 1. So I got the derivative of the bottom on top. So this would be the ln of the absolute value of u minus 1. Oh, no more du, sorry, plus c. Okay, the only thing left now is to substitute back in what u is equal to. So let's go back up. U is equal to the square root of x. So my final answer would be 2 square root of x plus 2 ln of the absolute value of the square root of x minus 1 plus c. So that one's tricky, right? You got to do u substitution. And on top of that, you also have to do long division. You know, that's a complicated problem. The main thing, the reason why I need to do long division is because of that square root of x. There wasn't much I could do with that. I can't do long division with the square root of x. But if I replace it with a u now and rewrite that, now I end up with that, with it in a form that I can do long division. Okay. The second thing we're going to do, so that's using long division to split a fraction up so that we can integrate it. The second thing we're going to go over is how to do inverse trig functions. So if you remember, when we take the derivative of the arc sine, it came out to be u primed over the square root of 1 minus u squared, and u is just the inside. Our tangent was u primed over 1 plus u squared. So if I'm working backwards, right? Again, if I have a fraction and I have u primed over the square root of 1 minus u squared, that's just going to integrate to be the arc sine of u. Or if I have u primed over 1 plus u squared, that's just going to integrate to be the arctangent of u. We can expand those rules or extend them out and end up with a little different version, which is this, is if you don't have a 1, it's not 1 minus u squared, but it's something else minus u squared, a constant there, then we can actually still integrate it. And I'll kind of show you why that works here in just a second. Same thing here. So instead of having a 1 plus u squared, if we have an a squared plus u squared, so a is just a constant, then we can also integrate it using the arctangent rules. So to show you why that works, oh, one other thing before we go on, sorry. Remember, the derivative of the arc cosine is just a negative sign. So for that reason, we're not going to have a separate rule for integrate. We're not going to integrate and get the arc cosine. We're always going to do arc sine every time. So you don't have to, you'll never have an answer that comes out to be arc cosine. Because if it did, we could just write it as being a negative arc sine. So we're going to simplify things. There's only two rules here. You have to know arc sine, integral rule for arc sine, and integral rule for arc tangent. Are the only two you ever have to worry about. So the book has this warm-up problem. I don't know that we need a warm-up problem. This is more just explaining why that extended rule works. Anyway, let's take the derivative of y equals arc sine of x over 2. Okay, so I'm going to start out right. The derivative of the inside, this is I've got that x minus 2, which is really the same thing as 1/2 x. So the derivative of the arc sine, I take the derivative of the inside on top. Well, the derivative of 1/2 x is 1/2 over the square root of 1 minus, and then it's the inside squared, so 1/2 x squared. So that's the derivative right there. I'm going to take it though and write it in just a little bit different form. I'm going to write it this way. This is the same thing as 1 over 2 square root of, and I got 1 minus, that'd be 1/2 squared, would be 1/4. And then if I think of it this way, I could think of the 2 as being the square root of 4 times the square root of 1 minus 1/4 x squared. And the reason why I did that is because now I can times through by the 4 because they're both square roots. So if I distribute that 4 through, I end up with 1 over square root of 4 minus x squared. Okay, so think back to that rule that we just talked about, the extended rule. So go back to here. Okay, think about this extended rule. Look at this right here. Right? So in this case, 4 would be my a squared, and x would be my u squared. And then I have to have that on top. So if I were working backwards, if I get given this problem, I'd think of it this way. It'd be 1 over the square root of, and write 4 as being 2 squared minus x squared. Okay. So look at that rule again. 2 would be a, and x would be u. So it ends up being the arc sine of x over 2 plus c, which is exactly what I started with. So this is just a way to deal with it. Mainly, that extended rule just deals when that number is not equal to 1. So if that number is not equal to 1, we have to approach it a little bit different way. We have to figure out what a is, and then we have to take it from there. And I'm going to show you a couple of tricks that'll make these problems easier. Again, a lot of times the hardest part is recognizing when to use this method. But once you recognize it, if you follow these little tricks, they're actually not bad, the arc sine arctangent problems. So let's go through a few of these. So I have the integral of 1 over square root of 4 minus x squared. So first of all, for this so we're going to start here to see if it's an arc sine problem. I would suggest this. Figure out what a would have to be. So that would have to be, what do I square to get 4? So off to the side, I'm going to put a would have to equal 2. Right, because 4 is 2 squared. Okay, and then u is whatever I have to square to get x squared. So in that case, u would equal x. And if I take the derivative, du, right, well, I'm going to do it, instead of saying du, I'm just going to say u prime. U prime would equal 1. Well, look what I have on top is 1. So if you're following the pattern there, I have to have a squared minus u squared, and then I have to have u prime up on top. So this fits it all. So now I just plug all those things into my integral. So I have the arc sine of, and it's just u over a, so that would be x over 2. Plug those two things in, and we're done. Let's give this next one a try. There's nothing up. By the way, if that dx is up on top, you can rewrite it this way. So I'm going to write it as being the integral of 1 over, I'm going to switch the 25 and the 4x squared around. So I'm going to write 25 as being 5 squared plus, and the 4x squared would be 2x squared. What I'm hoping is this fits the arctangent. And then the dx up on top is the same thing as having the timesing by the dx over here. Okay, so look back up there. Start out, what would a have to equal? Well, a would have to equal 5 in this problem. That's what I'm squaring to get the 25. What would u have to equal? U would have to equal 2x. So that means u prime, or the derivative of u, would have to equal 2. Okay, so we're pretty set up here. I've got the 5, I've got the 2x, but I need the derivative of u of the 2x up on top. Well, I have a 1 up there. I need a 2. So I'm going to times by 2, get a 2 up there, times by 1/2 out there. Okay, and now on top, I've now got the derivative of u up there. So we should be all set up and ready to integrate. So this is going to be 1/2. Now make sure you follow the rule. Make sure you have the rule here in front of you. It's 1/2 times by, and this is a part we forget a lot, it's 1 over a. Well, a is 5. So 1 over 5, arctangent of u over a, so that'd be 2x over 5, plus c. Okay, I got my answer. Hey, a really common error, when we do arc sine, you don't have that fraction out in front, that 1/5, that 1 over a. It's only when you do arctangent. So a lot of times we forget that, right? Because over here on arc sine, we didn't do 1 over 2. It's on arctangent. You just have to remember that little piece. So again, this comes down to more memorizing, right? Hopefully we're making flashcards and memorizing here. Okay, let's go up to number 5 up there. Let's give it a try. I'm going to erase this other stuff just to give myself a little bit of room. 5 is going to require a little more space. So let me just erase this. I'm going to slide that over just to make it a little bit easier, a little bit more room for us to work here. Okay, so if you look at this problem, this is probably going to be an arctangent, okay, is what it looks to me. And the reason why is because if you look up here, I've got a constant on top and I have the x squared on the bottom. So I'm going to take it and start out first by saying what a is. Well, a is what you square to get 3. So off to the side, I'm going to say a is the square root of 3. Right? We're thinking of this as being the square root of 3 squared. Plus, what do we square to get 4x squared? That'd be 2x. So u is equal to 2x. That means that u prime, or the derivative of u, is equal to 2. Okay, so now we got this. It's almost set up for an arctangent problem. My problem is I have an 8 up on top, and I want a 2. So I'm going to think of that 8 as being 4 times 2. So I can factor the 4 out in front. So now I have 4 integral from 0 to 1/2 of 2 over square root of 3 squared plus 2x squared. Okay, we're all ready to integrate. So now I'm going to have 4 times 1 over a, so 1 over the square root of 3, times the inverse tangent, or the arctangent, or inverse tangent, however you want to write it, of u over a. So that would be 2x over square root of 3. And then we have to evaluate that from 1/2 to 0. Okay, so let's plug in our numbers here, find out what we end up with. So now I have 4 over the square root of 3 times the inverse tangent, or the arctangent of I plug a half in there, 2 times a half is 1. So 1 over the square root of 3 minus 4 over the square root of 3 of the inverse tangent or arc tangent of, if you plug 0 in there, we just get 0. Okay, all we have to do now is evaluate what is the arc tangent of, what's the inverse tangent of 1 over the square root of 3. Right, so you draw your triangle to get 1 over the square root of 3 for the tangent. It's got to be this triangle. It's got to be the 1, 2, square root of 3. You get that. There's also be the square root of 3 there, sorry. Okay, so we come down here. That is, so to get that angle right there, right, is pi 6. So that ends up being pi 6 right there. So I have 4 over the square root of 3 times pi 6. That's what the inverse tangent of 1 over the square root of 3 is. Minus 4 over the square root of 3 times by the inverse tangent of 0. So inverse tangent of 0 comes out to be 0. It's at 0 degrees, so it equals that. Okay, and now you can simplify from there. I'm just going to leave it like that. So these can be long, kind of, especially if you have to evaluate it. They're complicated. But if you guys are good at trig, you'll do just fine. Key things here, just when you're doing these problems, make sure you start out with this, like what is up here, what is a equal to, what is u equal to, what is u prime equal to. That simplifies it a lot. What makes it even more complicated is we still have to remember all those other techniques we've done. Like if you look at number 4, this looks like that last problem, right? It's almost exactly the same. I just have an 8x up, I have an x up on top. So a lot of times we think, hey, this is a arc tangent or inverse tangent problem. The thing is, what is the derivative of the bottom? Well, isn't the derivative of the bottom 8x? This actually is just an ln problem. This is the ln of, I don't need the absolute values because that's always positive. This is just an ln problem. So we got to be careful not to automate, not to jump to conclusions. Make sure you think about that. I would personally always check to see if it's an ln first. This is a lot easier to integrate than what we just did, right, with the arc tangent. So what is the derivative of the bottom? If I have it on top, great, it's ln. If it's not, then we can check to see if it's an arc sine or an arc tangent problem. Again, this one looks a lot like that one, but the difference is this is not ln, right? The derivative of 4x squared is 8x, not 8x squared. Also, this is not an arc tangent problem because down here u would be 2x, and the derivative of 2x is not 8x squared, and I can't make that 2x. So these are tricky because they're all they all look really similar, but they're all just a little bit different. So this is one like I did at the very beginning, right? The degree of my bottom is the same as the degree of the top, so we can do long division, split it up. So let's do long division. So I'm going to go 4x squared plus 3. I can divide that into 8x squared. So we have to times 4x squared by to get 8x squared, be a 2. So it'd be 8x squared plus 6, positive 6. I have to change the signs. So ends up being a remainder of negative 6. So now I have the integral of 4x squared minus dx minus the integral of, and I take my remainder, 6 over what I was dividing by, which is 3 plus 4x squared. This is exciting. You guys are going to love this problem. So integrate 4x squared, that just comes out to be 4x cubed over 3. Oh. Hey, I just made a mistake. Did you guys all catch that? Let's come back up here. It's not 4x squared, right? Sorry about that. It's 2. That'll make the problem a lot easier, right? That was what I got up here, was 2 with the remainder of a minus 6. So this would be the integral of 2 dx, which is 2x, minus. Now I've got to integrate this. Hey, this is now an arctangent problem, and I'll show you why. I would say a is the square root of 3. So a equals the square root of 3. And u equals 2x. That's what's being squared to get 4x squared. The derivative of u equals 2. Well, I have a 6 up on top. I can make that a 2, right? So this is 3 times 2. I'm going to factor the 3 out. So it's minus 3. And then I just have a 2 left up there. So now this is all set up for an arctangent, right? A is the square root of 3, b or u is 2x, and the derivative of u is 2. So now we can integrate that. This is the arctangent or the inverse tangent of, oops, I got the 1 over the square root of 3. So 3 times 1 over a, that'd be 1 over the square root of 3. Arctangent of u over a, so that'd be 2x over the square root of 3 plus c. How fun is that? Like we could do log division, we could do arctangent all in one problem, right? It can get tricky, it can get pretty complicated. Let's look at number 8. Okay, so if you look at 8, so it looks a lot like an arc sign because that's the square root of 4 minus x squared, right? And a would be, what do I square to get 4? So a would be 2, and then u would be x. The problem is the derivative of x is 1. I don't have a 1 up on top. So that's what's preventing it from being an arctangent. So instead, I'm going to take it and try to split it apart. So I'm going to write it this way. I'm going to do the integral of x over square root of 4 minus x squared plus the integral of 4 over square root of 4 minus x squared. Okay, and now I'm just going to integrate these separately. Well, this one over here is actually just a reverse chain rule problem. Look at the derivative of the inside of this. It'd be a minus 2x. I can make that a minus 2x. So I'm going to times by negative 2 on the inside, by negative 1/2 on the outside. So I have negative 1/2 times the integral of negative 2x. And I'm going to move that 4 minus x squared up to the top. Let's make it a negative 1/2 power. Let's do this part first. So now this is my hook-on factor. It's the derivative of the inside. It's going to go away. So I have negative 1/2 times by 4 minus x squared. Add 1 to the power. A negative 1/2 plus 1 is 1/2. Divide by 1/2, which means I'm going to times by 2 out here. Okay, then over here, this now is an arc sign, right? A would be what do I square to get 4, which is 2. U is what do I square to get x squared, which is x. And u prime would be 1. So we're all set up other than I don't want the 4 there. So I'm going to bump the 4 out in front. So it's going to be plus 4, and then it's going to be an arc sign problem. 4 arc sign of u over a, so x over 2. Yeah, we should be there. So plus 4 arc sign of x over 2 plus c. We got our answer. All right, so these are complicated. Sometimes you're going to do multiple things. In this case, we're going to do multiple things, right? I split it apart and ended up being a reverse chain rule, which we've done before, and an arc sign, which is new for us this time. Again, this is probably of any section we ever do, this is probably the most challenging integration problems. It's not because any one in particular is that hard, but it's just a combination of all of them make it extremely difficult. Okay, so we've got a couple more, just kind of like, I wouldn't call them weird, but just different examples that you don't run into all the time. And the first one is this completing the square defined 1 over x squared plus 4x plus 8. So I'm going to kind of show you how we would do this. We're going to use a technique that you guys have learned before. Way back when you took Math 2, we learned how to complete the square. You may or may not remember, but I'm going to write the problem this way. I'm going to write it as being 1 over, sorry about that. Let me try again. Okay, so we're going to write it as being 1 over, and I'm going to put the 8 first. 1 over 8 plus, and then I'm going to put parentheses. I'm just going to group that x squared and the 4x together. Plus, I'm going to leave a blank right there. What I want to do is make this into a perfect square, that inside part. Perfect squares mean they factor like this, right? They factor to be I want it to be one of those. So the way you do that is you always take this middle term right there, the 4, you always divide it by 2 and square it. So 4 divided by 2 is 2, 2 squared is 4. So I have to add a 4 right there to make it a perfect square. So I'm going to add 4. But now I've changed the problem. So over here, out here, I'm going to subtract 4 or add a negative 4. Okay, now we're going to take that and rewrite it. And what we'll end up with eventually is we're going to end up with an arctangent problem. And I'll show you why here in just a second. So I have 1 over, I got negative 8 plus negative 4 plus 8, which is 4, plus, and then that factors to be x plus 2 times x plus 2, or x plus 2 squared. So we end up with that. Okay, now off to the side, here's what I'm going to do, right? A is what do I square to get 4, and that's 2. U is equal to x plus 2. And then u prime equals 1. Hey, well, I've got a 1 up on, I should have my integral sign in here, sorry. I have a 1 on top, so I'm all set up to integrate this. So this just comes out to be the arctan. So 1 over, it's 1 over a, so 1 over 2, arctan of u over a, that would be x plus 2 over 2 plus c. Okay, and I got my answer. Tricky, right? I know I'm putting a lot on your plate. As you go through the problems, make sure you look at the examples a lot. Again, a lot of times the hardest part is deciding like which technique to use and when. Hey, example 10 is a lot like example number 8. See, I have the x plus 4, and we think of this almost as being a single term, and so I split it up. 10 is just like that. So you have the 3 minus x over the square root of 1 minus x squared, so we can just split it up. So I'm going to split it up to be the integral of 3 over the square root of 1 minus x squared minus, I should put a dx in there, minus the integral of x over the square root of 1 minus x squared. So that first part now I can do, that actually is an arctangent. So if I'm looking at this, right, my u, I'm going to put it up here, my a, excuse me, what do I square to get 1? So my a would just be 1, u would equal x, and u prime, or the derivative of u, would equal 1. Well, the only thing I have wrong is I have a 3 there, so I'm going to move the 3 out in front. And now if I move the 3 out here, that means I'm all set up now for arc sine. So this would be the arc sine of u over a. That would be x over 1, so just x, minus. Now I've got to integrate this part. Well, don't forget the other techniques we've done in previous sections, right? The derivative of 1 minus x squared is a negative 2x. So we can actually do reverse chain rule. I'm going to make that a negative 2. I'm going to make this a negative 1/2. I'd actually change that to a plus 1/2. Now I'm going to rewrite it. So I have plus a half integral of negative 2x times by 1 minus x squared dx. This is the negative 1/2, sorry. I moved it up to the top, right? Okay, this is my hook on factor. It's just going to go away as we integrate. So I have plus 1/2 1 minus x squared to the positive 1/2 divided by a half, which just means I'm timesing by 2, plus c. Still have that 3 arc sine of x out in front. Sorry about the writing. Okay, those 2's would cancel out. And that should be my answer right there. I mean, we could do a little bit of simplifying if you wanted to, but we should be good to go. So that one wasn't that different from example 10. Okay, really similar to that. All right, now the last one we're going to do, we're going to get really crazy here. I'm going to show you another technique to do this. And this doesn't come up very often. I'm going to erase this over here. But it can. So let's try this example 11. Okay. So I have 1 over e to the x plus 1. So this is not an arctangent or an arcsine because at least not in this form, because I can't rewrite the e to the x over 1 as being something squared. What I can do is this. This is a little bit tricky. You know, it's almost gimmicky, but again, sorry, it's just the way we do it. So up on top, I'm going to write it as being 1, and I'm going to go like this. I'm going to add an e to the x to the top. I can do that as long as I also subtract an e to the x from the top. The bottom I'm not changing. So it seems really weird, but all I did up here, right, is I added e to the x and I subtracted e to the x. You may be asking why we would do this, and that's a legit question. I'll show you why here in just a second. What I can do now is I can take the problem and split it apart. So I'm going to write it this way. I'm going to write it as being the integral of 1 plus e to the x over e to the x plus 1 minus, I'm just going to split it into two separate integrals, the integral of a negative or minus e to the x over e to the x plus 1. Okay, the reason why I did this is if you look at this part right here, hey, 1 plus e to the x over e to the x plus 1, it's the same thing over the same thing. That's just 1. So really end up with the integral of 1 dx. Okay, over on this part, minus, look at the derivative of the bottom. The derivative of e to the x plus 1 is e to the x. So this actually is an ln problem. So I can go minus the ln of e to the x, and I don't need the absolute values because e to the x is always positive, and if I add 1 to it, it's always positive. Integrate 1, so I end up with x minus the ln of e to the x plus 1. Okay, this is a challenging section. You know, a lot of these problems are not obvious on what you should do, and a lot of them look alike. This will be hard, and I recognize that. Make sure you're helping each other. Make sure you work together. I will make sure the solutions are available so you can check those. And then I also want you to send me questions. I'll talk to you more about that in a separate message, but send me questions and I'll make sure to go through those the best that I can. Anyway, thanks for sticking with me and going through all these. This video will also be on Canvas, so you can use it there.